think we're getting close. So,
recording in progress.
Okay. So then it's my pleasure. Welcome everyone to welcome you to this session here at LPHYS. And the first talk will be given by LPHYS'23. He is from the Australian National University in Canberra, Australia. And the title you can read yourself. I think it has changed a little bit compared to the abstract, as far as I
understand. And thanks, Thomas, for noticing this. I just wanted, I want to welcome everyone. Thanks for coming. And that's right, the title changed a little bit, but I thought it's more descriptive. And along with this little cartoon characters, it allows me to explain better the main topic of this talk, which is introduction of a novel tool for the second metrology at FAL, which can do this on a shot-to-shot basis. These are the list of my collaborators for this project, and as you will see, they cover pretty much all 4 continents. And this work is based on 4 recent publications. Here is the outline of my talk, and as usual, the first question one has to ask why we are doing this, and the answer is we want to characterize the timing of atomic ionization by means of the phase-to-time conversion. It's been a very popular topic, probably over 15 past years, and there have been developed several techniques for doing this. And this experimental toolbox probably very well familiar to the audience, but I will have to give the methodical introduction to explain how the techniques that we develop is different from what is in this toolbox. As a theorist, I will be using my own tools, and I will introduce the tools during the talk because they are essential for our derivations. Our numerical results include atomic and molecular hydrogen. And as a possible extension of this technique, we'll consider shape resonances in atomic xenon and molecular nitric oxide. This slide gives a graphical introduction of the concept of photoemission time delay, also known as a Wigner, Eisenwood, and Smith time delay. Very simply, suppose we have a photoelectron wave packet which expands, and on the way out, it propagates through some central potential. By propagating through this central potential, photoelectron acquires a scattering phase, and this scattering phase contributes to the total phase of the outgoing wave packet. This wave packet propagates in such a way as to keep this phase stationary, which means the energy derivative of the phase remains close to 0. And this equation gives the trajectory of the photoelectron, and it seems that it starts its motion, not at time 0, but it starts its motion with some offset. And this offset is very easy to visualize by back propagating of the photoelectron trajectory to the origin, and we will see that intersect of this trajectory with the 0 coordinate takes place at some time, which is called Wigner time, and it can be expressed by a simple formula attributed to Wigner and its co-workers. Wigner derived this formula for electron scattering. Photoemission is slightly different. In photoemission, the photoelectron can acquire some of its phase right at the instant of its birth. And most accurately, this phase can be expressed as phase of the complex dipole matrix element. What is described here is a Gedanken experiment or thought experiment. No one can actually do this, In reality, they use different techniques, and historically, the first technique used for this measurement was attosecond streaking, where they use the optical wave to accelerate or decelerate the photoelectron, and depending on the moment of its burst, its energy either decreases or increases. So it's a time to energy conversion. And if we stick together the photoelectron spectra at different moments of its burst, we will get something which is known as a spectrogram. And this figure is the most celebrated example of the photoemission time delay in neon in two atomic shells, 2s and 2p. And if you analyze the spectrograms carefully, we will detect the time delay difference between these two shells of 21 plus minus 5 attoseconds. Attosecond streaking can be done in two different ways, either with linear polarized light or circularly polarized light. With linear streaking, we convert the time to the energy of the photoelectron, but with angular streaking, we convert the time of the burst to the angle of photoelectron emission. Circular streaking has certain advantages over the linear. Vector potential remains nearly constant if you look at this diagram during most of the cycle of the laser pulse, whereas in angular linear streaking, the useful period is probably time is probably quarter of the period of the laser pulse. And also, angular streaking has a very simple conversion mechanism. It depends only on the frequency of the rotating field, whereas in linear streaking, it also depends on the magnitude of the vector potential. So angular streaking has some advantages. In practice, the most common technique to characterize the timing of photoemission is the RABBIT, which is acronym for reconstruction of attosecond beating by interference of two photon transitions. In these techniques, the odd harmonics of the laser frequency, the two neighboring odd harmonics are used to ionize the atom, and then one laser photon is either added or subtracted to ionization process to produce what is known as the even sideband in the photoelectron spectrum. And because there are two different quantum pathways leading to essentially the same final state, this quantum path interferes, and the phase of this interference depends on the Wigner phase. The interference formula contains twice the laser photon frequency, and the RABBIT phase contains the Wigner phase added by some instrumental phases, which in practice are hard to control, and experimentally one tried to eliminate these phases by performing pair measurements. For instance, in the first experiments on neon, it was the relative time delay between 2s and 2p shells. Subsequent measurements used a pair of atomic species. Now they used different directions on the same atomic target. Finally, they implemented what is called polarization control of RABBIT when initially copolarized XUV pump and infrared probe, their polarization axis allowed to rotate relative to each other. Very recently, they do the RABBIT with circularly polarized pulses, and by changing the helicity of these pulses, they also were able to do the relative measurements. So what I will be talking about is attosecond angular streaking or XUV ionization was introduced for a different purpose. in the techniques which I described before, the delay between XUV pump and infrared probe was tightly controlled. There are situations when this delay is not known, and this is the situation of free electron lasers, where the XUV pulse is stochastic and it can come at any particular time. There is no prior knowledge of this time. And this technique was introduced initially to provide this control, to provide the timing information of XUV pulse. It was not concerned with timing of ionization process as such. So, depending on the arrival time of the XUV pulse, which is short and compared to terahertz radiation, there are two situations, 1, 2, 3, when this pulse is displaced relative to the terahertz probe, the photoelectron momentum distribution looks very different. And from this difference, one can infer the actual moment of the arrival of this pulse. There is a terahertz radiation was very handy because in initial measurement on first free electron lasers, the jitter or the arrival time can be hundreds of femtoseconds. So terahertz radiation with extended period was very useful for this measurement. How to understand what's the theoretical interpretation of this attosecond angular streaking with XUV ionization? I call this ASX. Briefly, it's easy to remember because ASX also stands for Australian Stock Exchange. Now, we also recall this principle of the stationary phase. In the strong field approximation, this phase contains only a photoelectron momentum and the vector potential. And for a particular geometry of the circular field and photoelectron detected in polarization plane, this stationary phase trajectory is very simple. It just becomes this cosine equation where the displacement of the photoelectron relative to the its free electron value depends on the detection angle phi and time delay between the XUV pulse and infrared probe. So far, everything is very simple, but one element is missing here, and this is photoelectron phase acquired by propagation and the birth. So the idea is to reintroduce this phase to this isochron equation, and the way we do is the following. We consider photoelectron momentum distribution in polarization plane. Left graph shows the Cartesian coordinates, right graph in the polar coordinates, and we see in the right graph that left and right, or up and down, 0 degree and 180 degrees momentum distribution is displaced, and it's displaced from the isochron by the maximum vector potential in the infrared probe. Now, we introduce the central momentum, K plus and K minus, which correspond to 0 and 180 degrees, and look at the isochron equation specifically for 0 and 180 degrees. And we reintroduce this streaking phase into this equation. Now, and this is the diagram which depends on the time delay between XUV and IR, and it shows on the top of this graph. And we start to vary it. We vary it gradually by some increment of quarter of femtosecond, and we will see that this diagram moves up and down. And if we plot the central momenta of the 180 degrees and 0 degrees momentum lobes, and they fall on the two branches of the isochrons. If the scattering phase equal to 0, then isochron branches intersect exactly at pi over 2. But if there is some streaking phase, then the intersect will be offset by this phi-s value, which presently it's 2/10 of the radian. Now, this way, it's very easy to obtain this streaking phase from this measurement. But we have to calibrate this technique. And to calibrate this technique, we just make a comparison with rabbit phase, which is known very well from simulations and experiment. And as a test case, we consider hydrogen atom, which is known very well. The only point that we have to recall is that rabbit signal oscillates with twice the laser frequency, whereas the streaking signal oscillates with single streaking frequencies. So rabbit phase has to be compared with twice the streaking phase. And when we make this plot comparison, this is nearly perfect and very good agreement with analytical model, which works fine for heterogenic targets. And if we screen the Coulomb phase of the hydrogen atom, and we get something which is known as Yukawa atom, and both rabbit phase and streaking phase, they all but disappear, which shows that colonic origin of the streaking and rabbit phases. And interestingly, the rabbit phase and time delay are negative in Coulombic system. So it's not time delay, it's actually times advancement. But there was something of cheating in this technique, because I presume in this isochrone analysis that we can control the time delay between XUV pulse pump and infrared probe. In fact, they are not known. So we are not in a position to vary them systematically. What we have in reality is just random arrival of with variable delay between infrared pulse and infrared probe and XUV pulse. So we have to derive the streaking phase for every single tau value. We cannot use all the set. By doing so, we lose considerably in accuracy. This dotted line show the accuracy. If we use the whole set of tau values individually, we get quite significant deviation from this mean value, but this deviation is still tolerable. It's probably not more than 10%. It's a sufficiently good accuracy. To do so, we need to know the A naught, which is the magnitude of the vector potential, and we need the absolute timing scale. We need time zero for this measurement. A naught can be determined from the maximum displacement of the up and down loops in photoelectron momentum distribution, and the time zero can be obtained from this value, provided the scattering phase or streaking phase is zero. And we absolutely sure that if photoelectron energy is sufficiently large, then the streaking phase is zero. Because fast photoelectron cares very little about any scattering potential. It just propagates without any scattering. That's a very well-known physical effect. So our next target is molecular hydrogen, and if the photoelectron energy is not very large, then there is no difference because we are in a weak interference effect. So hydrogen molecule is essentially atomic-like, and this is very simple to understand from this interference pattern. When the Breuer wavelength is much larger than interatomic distance, there is no any interference, and in this measurement, the photoelectron momentum distribution in parallel orientation and perpendicular orientation of molecular axis relative to the polarization axis, they look very much essentially the same. However, if we increase the photoelectron energy, we enter the medium interference when the product of the photoelectron momentum and interatomic distance is approaching unity. Then parallel orientation and perpendicular orientation becomes noticeably different, especially if we look at the integrated angular profile. And finally, if we increase the photoelectron momentum further, we enter the strong interference effect where the parallel orientation, perpendicular, they are manifestly different. We see these interference fringes in parallel orientation, and they're very well pronounced in the integrated signal. Now, if we compare the streaking phase and time delay between the hydrogen atom and hydrogen molecule, we will see that for low photoelectron energies, they're essentially the same. But for interference factor approaching unity, we get a very significant deviation between parallel and perpendicular orientations. Perpendicular remains essentially atomic-like, but parallel changes the sign of the time delay. And it's very important physical result, because in Coulombic systems, the atomic time delay is always negative, and in molecular hydrogen, in parallel orientation, it becomes positive both in rabbit and streaking. And this effect can be attributed to the confinement trapping of the P wave between the nuclei, where this interference product approach 1 unit of pi, and it's very well documented effect. Finally, conclusions. What I showed in this talk, I introduced the concept of general principles of attostreaking, streaking of XUV ionization. Initially, it was used to characterize stochastic pulse arrival at free electron lasers. It was introduced initially within the framework of the strong field approximation, solely for mapping pulse arrival time to photoelectron momentum distribution. We went beyond the SFA and we reintroduced the scattering of photoemission phase by a way of modified isochron equation. We reintroduced the streaking phase to this isochron equation. And by running numerical simulation on atomic hydrogen with weak micrometer probe superimposed on XUV pulse, we truthfully retrieve the streaking phase by controlling XUV IR delay. This is very accurate determination. Unfortunately, it cannot be used in the shot-by-shot measurement. Random shot retrieval is also possible once the magnitude of the vector potential and time zero is established. We can establish them from the photoelectron momentum distribution at sufficiently large photoelectron energy where the scattering phase goes to zero. Attosecond streaking phase and rabbit phases match. Time delay in hydrogen atom supports analytic theory. When we do the similar simulation in molecular hydrogen, we identify strong interference and molecular axis alignment effects. A slow photoelectron behaves in the slow photoelectron regime. Hydrogen molecule behaves essentially as an atom, but if we increase the energy, we start probing interference effects. Finally, as a possible extension of this work, we will be looking at shape resonances and photoionization cross-sections of atoms and molecules. Shape resonances are unique objects because time delay can be extracted directly from photoionization cross-section, and it gives very robust test on the photoemission time delay. And this test has been applied to nitric oxide. The time delay was extracted in LCLS by this attosecond streaking of XUV ionization. There is some disagreement between theory and experiment, which needs to be resolved. And also another example is the shape resonance in 4D shell of xenon. Here, there is also some noticeable disagreement between theoretical prediction and experiment, and we will be working on resolving this. That's probably the end of my talk. I thank you for your kind attention, and this talk is open to questions. Thank you.
Yeah, thanks very much, Anatoly, for a very nice and also instructive talk and great results. Congratulations. Are there questions? We have almost no time because I think you used up all your time for talking, but maybe a short question. No question?
Okay, so if any questions, you can email me.
Always later. Okay, perfect. Thanks a lot. Then we can stay in time. I would have had questions, but maybe after the session. Okay. Then we move on to our next speaker and talk. This will be given by Weichao Liang from the College of Physics and Optoelectronic Engineering in Shenzhen University in China. And the title, maybe have you shared already? It works. Yes. If the title has not changed, okay, here it is. Strong field effects on time delays in correlated ionization. Looking much forward to your talk. Please go ahead.
Thanks. Thanks for giving me this opportunity to introduce our research study on the strong field effect on the time delay in correlated ionization. I'm Weichao Liang, come from Shenzhen University. This is the outline of my today's talk. First of all, I will give a brief introduction for the background of streaking. Actually, the last speaker have already given some background. And most importantly, I will give a detailed introduction for our theory. Our theory consists of two parts. The first is the time delay. I'm sorry?
Please, everyone not talking, mute your microphones, please.
Okay. Our theory, the first theory is the time-dependent, is based on the time-dependent Schrödinger equation. The next theory is our model. We call it as the conditional two-electron model to account for the strong field effect on the time delays. After introducing our theory, I will present our numerical results. But during this, I will also present our recent study on the multiple photon double ionization. And then I will give a detailed introduction for the strong field on the time delays. At last, I will conclude my talk. This is the typical streaking spectrum we calculated. When we exposed an atom into the XUV pulse and RR lead pulse, the momentum spectrum will depend on the time delay between the pulse delay. In this momentum streaking spectrum, a lot of interesting physical information is included. We can extract the pulse envelope, the pulse waveform, and the time delay. In the simple picture, when an electron is exposed to the when the photoelectron is exposed to the IR leader pulse, it will be accelerated by the vector potential. The momentum shift is exactly the vector potential when the photoelectron sees the electron sees the vector potential. But in the real case, if the ejection of the wave packet have any time delays, the electron will see the electron will see the vector potential at a different time. So when we comparing the momentum shift, with the vector potential, we can extract the streaking time delays. In the theory, the pulse delay is accurately known, so we can extract one absolute time delay. But in an experiment, in the experimental measurement, usually the pulse time delay is not accurately known. So in the pioneering experiment on neon, the experiment measures the time delay between the photoanalysis time delay between the 2S state and the 2B state. The time delay of 21 attoseconds triggered a large number of debates. Only recently, this difference is attributed to the seek up, to the influence of the seek up channels. As far as we know, until now, the complete AB initial treatment for the streaking time delay is still restricted on the 2-electron helium, and on the 2-electron targeted helium. Lunatics calculations have been confirmed. Lunatics calculations have been confirmed. Lunatics calculation 10 years ago has recently been confirmed in 2017. The accuracy, the difference between the theoretical calculation and the experimental measurement is within 1 attosecond. Recently we have extended the concept of the time delay to the strong field regions. Previously, most of the study is based on most of the previous study on the time delay is focused on the is listed on the weak active LPHYS region. Our theory is based on the accurate. Our theory is based on the accurate solution of the numerical of the Schrödinger of the Schrödinger equation in the four-dimensionality. The 2-electron wave functions is expanded into the harmonic coupled harmonics. The radial part is further described by the FEDVR method. The time propagator, we use the split Lantrus propagator to propagate the wave function, 2-electron wave function. As we know in the theoretical calculations, when the pulse is long, usually the 2-electron will go to very far from the core. We need a large box to describe the wave function. This is very challenging. So we use a very popular method. We call it the wave splitting technique. We divided the wave function periodically into inner region and outer regions. The inner region is still described by the split Lantrus propagator, but for the outer part, we use the Volkoff propagator, which means we will negate the influence of the Coulomb potential. This way, we can use a small box to describe the full propagation of the whole wave functions. But when we apply the wave splitting method to the double analysis, actually we find there are still many challenges. One of the challenges is that the electron in the single analysis in the outer region, we not only have the double analysis continuum, we have the single analysis continuum and the double analysis continuum at the same time. In the outer box, the single analysis continuum can be further. The electron in the single analysis continuum can be further transformed to the double analysis continuum. And the second challenge is that the electron actually in the outer region, we will neglect the electron correlation in the outer box. But sometimes the electron correlation in the outer box is also important. Next, I will give a brief introduction for our recently study for the multiple photon double analysis problem. Previously, the double analysis have been extensively discussed in the 2 photon regions. But in the multiple photon rays, it's the corresponding theoretical study is very lacking. Here we have extended the photon number from 2 to 5. Actually, when the photon number is increased, a lot of sequential ionization paths will open. By absorbing some photons, the first electron can be ionized, leaving the next electron in the bound state of the helium plus. Alternatively, the bound students can the bound electron can be excited into the first excited state, for example, 2p state, instead of staying on the ground state. So the first sequential path, we call it the direct sequential ionization passes. If the bound electron is in the excited 2p state for helium plus, we will call the sequential ionization path of the ERR ionization path. For different sequential ionization paths, we can distinguish these passes in the energy spectrums. Actually, the electrons from different paths will have special energies. So in the energy spectrum, we can clearly identify the direct sequential ionization paths and all the ERR sequential ionization paths. Very interestingly, for the 3-photon double ionization, double ionization, we can identify the two sequential channels. We find that the two kind of sequential channels are comparable, which means the DSI channel are comparable with the ERR channel. In the 2-photon double ionization, for the 2-photon double ionization, usually we can only find the one sequential ionization channels. Especially for the 3-photon double, we want to study the electric correlation effect in the multi-photon double ionization. So we vary the path length systematically. This is the first column is the first column is for 5 cycle linear path. The second column is for the 20 cycle path. The third row is for the 100 cycle linear path. As you can see, for the longest path in the third row, both sequential peaks can be identified when the electron angle is 0 or 180. It means when the electron is when the two electrons are attracted in the same direction, forward to forward, or the two electrons are ejected back to back. No matter for these two modes, the sequential peaks can for both modes, the sequential peaks can be identified. One exception is for 3-photon double ionization. In this case, we can see that when the electron is even for the longest path, if the two electrons are ejected into exactly the same direction, we can't identify clearly the sequential peaks. Because in this special case, the second electron has a slower velocity than the first electron. I'm sorry, the second electron has a faster velocity than the first electron. So it will finally catching up with the first electron and has a strong correlation. This will change the energy. And we have used a classical trajectory monocular simulations to account for this electron correlation at large distance from the core. The CTMC calculation is calculated by Christoph. So, and we found that very surprisingly, this electron correlation at large distance also requires a very large angular momentum in our calculations. This is the angular distribution, the equal-energy angular distribution is on the compliant. For the 3-photon double analysis, if the calculation is not converted, we will identify a single peak here. Here. Our calculation has finally converged, so we find that the single peak actually split into a double peak here. Here shows the correlated momentum spectrum. These spectrum are very popular in the double analysis by the IR laser path. People have prefer to identify the so-called correlation or anti-correlation in the correlated in such kind of momentum spectrum. Next, I will introduce our calculations for our studies for the strong field effects on the time delay. As a check of our numerical method, we firstly try to reproduce previous calculation by Renat. We have compared our theory with the experimental measurement for the photon energy around 100 eV. And our result, this is our result. This is the experimental result. This is the result from Renat. You can see that all these results are typically within 1 attosecond. After confirming that our numerical method is valid, we now study a new case. The strong field streaking of helium at 40 eV. We increase the intensity of the XUV path to very high. This energy is very special. Here shows the possible ionizing passes. At the photon energy of 40 eV, the photon ionizing can be take place by absorbing one photon. So in this channel, we call it the direct sequential channels. If the XUV intensity is very high, another channel will open. After the electron absorbed the first photon, the second electron can absorb another photon and be excited from the ground state 1s to the 2p state in the helium plus, which means the second photon can induce to the core resonance. So this is the two photon excitation ionizing channels. When the intensity of the XUV path is very low, obviously we only have the PSI channels. These are our results for these are the streaking spectrum for different channels at a large XUV laser intensity. This is the direct sequential channel. This is the ER channel to the 2p state. This is the ER channel to the 2s state. We can see that for currently we have increased the laser intensity to 2 × 10⁻⁻XVI watt per centimeter square. At such large laser intensities, the signal of the ER channel is actually larger than the signal from the DSI channel, which means that the strong field effect really evolve. Actually, the inclusion of the strong field can also be clearly identified from the split of the peaks in the streaking trace. This such a splitting of the peaks actually have previously have been studied by Avery long time ago in a two electron in a reduced dimensional TDSE calculation. He Avery firstly predicted such kind of splitting. And actually, it is usually called the continuum autonomous splitting. This splitting is special because the ground states actually do not experience a Rabi oscillations. The Rabi oscillations only exist in the core. And shortly later on, such kind of AT splitting have been experimentally observed in 1995. The interesting thing is that after we increase the intensity of the active path, we found that the streaking time delay, both the streaking time delay of all channels can be very, very large. The core problem is that how to interpret, how to understand such a large, how to interpret such a large streaking time delay.
Sorry, your time is up. You have to summarize soon because it goes until 46. It's already almost a minute over. You have to come.
I'm sorry. Okay. I'm sorry. Actually, we have I still have many PowerPoint. I'm sorry. Okay, I will give a quick conclusion for our studies, and our studies show that for either our studies show that for the dramatically nonlinear effects on photo immersion time delay have been identified, and we found that the Rabi oscillations in the core can lead to both positive and negative streaking time delays. And we have built a conditional two-electron model to interpret such kind of time delay. Actually, and I have not shown the figure. I'm sorry, because I have used up my time. But the SAE calculation, and we found that the single active electron describing for anything will also break down when the intensity of the active path is very high. Thanks for your time.
Thanks very much for your nice presentation. Also, congratulations on the results. I think we are out of time, so we unfortunately have to move on. So people who are interested should just write you an email, or maybe after the session there's more time. But we have to move on to stay on our schedule, I think. So okay, thank you again, and then maybe stop the sharing and we put up the next speaker. Exactly. So this will be Dongyeon Kim from the Postech Institute in Pohang, South Korea. And the title, as you can see, is Simple Complete Characterization of Ultrafast Optical Pulse by Phase Preservation Autocorrelation. So please go ahead, looking very much forward to your talk.
Okay, thank you very much. Can you hear me well?
Yes, works well.
Okay, so thank you very much for introduction. So I'm Dong Kim from Postech and also Max Planck Postech Courageous Initiative. So today I'd like to share our recent results about characterization of ultrafast optical pulses. Okay, basically this work was published last year in Life Science Applications. So you can look up this paper for more details. Basically, here I'd like to mention some complete optical pulse characterization without spectrometers. Okay, so we call this method is phase-enabled nonlinear gating with uneven intensities. We simply name the penguin. Okay, so so in my talk, I'd like to share some motivation for this work Then I introduced penguin formalism. And then we demonstrated this method using 4 femtosecond pulse. And then I'd like to conclude my talk. Okay, so basically, laser technology has been advanced. So nowadays, people are very much interested in producing ultra short pulse through supercontinuum generation. So you can produce supercontinuum using a local fiber with gas being filled. And also you can use the multiplate, series of multiplates, thin multiplate, right? So we can make a broadband like this. And then people using waveform synthesis to introduce some phases between the spectrums so that we can make a single cyclic pulse and then this kind of pulse, and you can make a double pulsing with phase opposite direction and so on. So it is very important to characterize the ultra short pulse very well. Okay, so in the past, people have developed various methods. So one of the most popular one is cross correlation, right? So basically, you have some the pulse which we'd like to know, and then we gated that pulse with some gating function, and then we do autocorrelation, and then you have autocorrelation signal. And so in this case, in the case of this gate function will be the delta function, and then autocorrelation will be like the original pulse that we'd like to know, right? So recently, already 10 years ago, and the second isolated second pulse has been developed, and then that pulse have been used to characterize the ultra short pulses. Okay. Also, you can use tunneling ionization processes, right? And so this is a kind of example using the delta function type of gating, right? And so this is a direct sampling of the field, so you don't need any retrievable program at all. In that sense, it's very nice. But to have this attosecond facilities and the imaging things requires a lot of investment, and things are complicated. Okay, and so people for the characterization of optical pulse, people use the pulse itself for the gating. So that is called autocorrelation. This is the most popular way to characterize the optical pulse, right? So good example is the frog, right? So basically, this is the typical autocorrelation setup with a photodiode, but they replaced the photodiode with the spectrometer because when you use the autocorrelator, and then you're basically losing the phase information, so you cannot retrieve the phase information, so you cannot completely characterize the optical pulse. So they use the spectrometer, and then every time delay, you measure spectrums, and then put them together like a 2D frog diagram. And then basically you measure the spectrum every time. So you have a redundant data set from which you get the phase information, then you can have a complete characterization of the pulse, okay? But this is good method, but you need to run the retrieval program, so it cannot be used in real time. So for that purpose, people developed a spider, and this is good in terms of real-time diagnostic, but as shown here is optical shadow is more complicated than frog, okay? So these are good methods, but this is how the disadvantage, I mean, some weak point. Weak point is like, how about ultra fast pulses which does not ready? Okay, so spider and frog needs a spectrometer to characterize the pulse. And so, but one good example for the ultra fast electric field, which does not radiate, is plasmonic field. Okay, you have another structure, you shoot the optical pulse and so on, then you develop the electric field in near field. right? And then does not radiate. So typically people using P machine to immediate in P machine means you're collecting for electrons. So basically you're collecting the signal to probe the what's going on in the plasma field in near the non-structures. Okay, but then for this one, you need the P machine, you need the ultra high vacuum. The P machine usually very expensive. So so we need another method to deal with this non-radiating electric field too. So then we revisited interferometric autocorrelate setup. Okay, so basically we use a photodiode, and so we don't measure the spectrum, it's just measuring the electrical current. Okay, then we look at this setup, then we examine, I'll show you later, then we examine the correlation formula, then you realize that if you introduce imbalance between two arms, okay, we have one pulse, we have a beam splitter, and then you have two arms, okay, and then so it is collinear setup, so for interferometric setup, so to maximize interference, to increase the visibility, you want to have a 1-to-1 ratio. That's a typical way. But if you introduce asymmetry using neutral density filter, okay, then story goes different way. Okay, so then with this setup, you can have a phase information. Okay, so this is the generalization. This is autocorrelator equation for the this unbalanced case. So S is representing unbalanced, right? And so we have a since this parallel interference setup. So have a you have this field, and then this is order of the nonlinear process here, and then this is for intensity. Okay, this is the general equation for interferometric autocorrelator. Okay, you can expand it, and actually the formula becomes very complicated. So let's just look at the simple case, n equals 2 case. Okay, so like we get generate second harmonic oscillator. So even in this case, we have a 16 term. So these are already complicated, but if you can collect them very wise way, then you can have this kind of things. Okay, so this is the real value, and this is the real value, and this is real value. Okay, so we have this kind of term, but if you, but they are, so just forget the S. Okay, so forget that, then this term and this is complex conjugate. Also this value and this value is complex conjugate. So when the S equal 1 case, this is the typical case, it's a conventional case. In that case, I mean, this and this becomes real value, and this becomes a real value. As I mean, they are complex conjugate, and they develop and becomes a real value. So that, I mean, in this case, interpolation becomes the real values, and it losing the phase information. But if S is not equal 1, okay, then story different. Okay, these complex values and these complex values. So it contains the phase information. Okay, so this is I'm showing this one. So this is electric field. Okay, and then this is the autocorrelation signal in case of S equals 0.5. Okay. And so this is a component of the various components of the autocorrelation signal, all added up becomes like this one. And also this is shows the spectrum. And so this is showing the spectrum of this and this and this in spectral domain. Okay, so so this component case is real value, so the phase is constant. But in this case, this one and this one case, so this is complex, so that I mean you have the phase information. So we can use this one to extract the phase information, and then you can make the run the retrieval program. Then you can extract the phase information, and also you have intensity, so that you can have a complete characterization of the course. Okay, so suppose we use this term. Okay, this term can be written this way. So if you take, so we are filtering this component. So we have a filter, and then we have autocorrelation in frequency. Okay, then filter out this one, then make the inverse Fourier transformation will be electric field. Okay, then you use this one here to have a next step. Okay, so using this formula, you can have a retrieval program. And also you can have a Q factor to mix the previous step with the new step. It depends on the situation. Okay, so this retrieval program is very simple. And as is shown, within a few tens of iteration, you reach the error of like down to the 10 to minus 15. Okay, it's very quick, so it can be used in real time. Okay, so here we carry out the experiment to prove our method is correct. And so this is showing the comparison between our method and the conventional IFROG, interferometric frog method. So you use the 6 femtosecond pulse, and then you use the PBO, 10 micron thick PBO for the second harmonic generation. Okay, so this is IFROG measurement. Okay, this is S equal 1 case, as a typical, right? And you put the balance system for the maximize the visibility of the interferogram. Okay, so this is the measured IFROG signal. Then you use the retrieval program to have this one. Okay, so you notice the excellent agreement between measurement and retrieval. Then the program automatically gives you spectrum, right? So IFROG measurement is the red one. And the reference means is the spectrum of the 6 femtosecond pulse measured with a intensity calibrated spectrometer. Okay, so we have a good agreement between the reference and frog. And so here, so we also did the experiment with the penguin method, which we just mentioned 3 minutes ago. And you see the red one, the blue one is representing result by the penguin. So you notice that there's a good agreement between IFROG and penguin and the reference. And this one shows you time, actually pulse in time domain. Okay, so we have an excellent agreement between penguin and IFROG. Okay, so this one case is S equal 0.5 case for the penguin. You can choose various values for S. So basically, this slide shows you our experiment for different S values, starting from S equal 0.05 to the like S equal 0.94. It's almost 1. But as long as S equal is not 1, then you can use the penguin method. And then as you see here, we have a good agreement between IFROG and real values and the penguin. Yeah, so the red one is IFROG measurement, and then green one is the penguin method for each S values. Okay, so so basically penguin method works for any S values, not for 1. And so for the considering the noise issue, and we recommend the S value of around 0.6 for the best performance. Okay, so I'd like to conclude my talk. So basically, we introduced a new method called the penguin for complete calculation of optical course. It doesn't require no spectrometers. So, and then just use a photodiode, and so this setup is very simple. Basically, this is the interferometric autocorrelator. And then you just introduce the neutral density filter in one arm to break the symmetry between 2 arms. So you put the feed the silica here to compensate the dispersion in 2 arms. Okay, and because of the control density introduced dispersion. Okay, so basically you need to run the retrievable program, but it's very fast. So you can use video rate, and this one can be used for the non-radiative ultrafast fields such as nanoplasmic field and near field, which does not radiate. Okay, so this one published in this last year. So you have more information, detailed information over there. I'm sure you're welcome to see the paper, and also I recommend to use this one in your lab. So I'd like to thank my co-workers, and also I'd like to thank the funding agency, Korean National Funding Agency. Okay, thank you very much for your attention.
Thanks very much, Dong-Yeon, for this very nice talk, and also congratulations on this great results and staying perfectly in time, actually, in fact, also for your talk. So there's time for questions now, finally. Just raise your hand, or also type in the chat if you like, or just speak up. Just unmute and speak. If no one starts, I would like to start. So I was wondering what requirements you have when you apply your method. Do you have to scan? I guess there's a requirement you have to sample to long times also to get the full information. Is there a good rule of thumb how long you have to scan your autocorrelation to reconstruct the pulse faithfully or well enough? I guess it depends on how long your pulse or how complex it is structured, of course. No?
Yes, so basically, so basically, this is a simple setup, and you kind of normal practice as you do with this kind of thing. This is the time you require to get the data.
So, okay, so you have to
if you run slowly, okay, so you have a better signal to noise ratio.
Yes.
Okay, is better for that. But
okay.
I think there is no quite limitation.
No. So essentially, you have to
up to you how quickly you want to do, how fast you're going to do. Then it'll be more noisy. So that you have less information. Right?
Okay. Yeah. Thanks. There's another question. I hear something in the background. Anyone else? Yeah, the signal to noise is a good point. So is there some requirement how much signal to noise you need to get the reconstruction? Have you looked like as a function of signal to noise?
Yeah, so you have some. Okay, so this is we also study the noise, right?
Yeah.
So here is we introduce noise like 2%. Okay, and so even if 2%, like this is, this is error value. Okay, so when we don't have a error, and then you count down to like 10⁻16.
Okay.
So you have like 1% error here, so you can go to 10⁻3.
Okay.
So still, this value is not bad. So and the 2%, the few percent error still usable.
Yeah, no, this is fantastic. All right, thank you. Any other question? If that's not the case, then thanks, Dong-Yeon, again for a very nice talk. And we move on to our last speaker of this session, who is hopefully here. Xu Wang. Yeah, exactly.
Yes. Okay. Okay.
From the Graduate School of China Academy of Engineering Physics in Beijing. And if the title, so you are still sharing, I think, in the process of sharing, I will read the title: Isomeric Excitation of Thorium-229 in a Strong Femtosecond Laser Pulse. So very much also looking forward to your talk once it's once it's online or open. Yes, it opens
Can you
up.
see the
Yes.
PPT now?
It's still in slide mode. Okay, in edit mode. Now it's full screen. Perfect. Go ahead.
Okay. Yeah, it's a pleasure to have the chance to present our results on isomeric excitation of thorium-229 in a strong femtosecond leather pulse. Thorium-229 has attracted much attention in recent years because it has a peculiar nucleus. The first excited state of the nucleus, which is also an isomeric state, is only about 8 electron volts above the nuclear ground state. It is the least known nuclear state. It has potential applications especially in nuclear optical clocks. And also, it is a very interesting system that connects nuclear physics with atomic physics because 8 eV is also in the range of electronic transitions. This isomeric state can be obtained from nuclear decays, for them from alpha decay of uranium-233. 2% of the thorium-229 nuclei are left in the isomeric state. Or it can be obtained from beta decay of actinium-229. 14% of the nuclei are left in the isomeric state. We call these passive methods. And we are more interested in active excitation method. After all, active excitation and control is the basis of these potential applications. As nuclear physicists, we know that the active excitation of nuclear levels is notoriously difficult. Several attempts have been made to excite the nucleus using VUV light around 8 eV or 150 nanometer in wavelengths, but no positive results have been reported. An alternative excitation method was demonstrated using 29 keV synchrotron radiations to excite the nucleus from the ground state to the second excited state, which then decays preferably into the isomeric state. The excitation rate is 10 to the minus 11 per second per nucleus. It also has been demonstrated that to use laser ablated plasmas, to use a nanosecond laser pulse ablated on a material containing thorium-229, and the nucleus may be excited by the plasma electrons. The excitation rate is roughly 10 to the minus 5 per nanosecond pulse per nucleus. We have been considering this problem, that whether it is possible to excite the nucleus to the isomeric state using femtosecond laser pulse interacting with an isolated thorium-229 atom. As a strong field atomic physicists, we know that such an interaction will initiate an electron recollision process. That electron is pulled out by the laser field and driven away, but it has a chance to be driven back and recollide with parent ion core when the laser field reverses direction, leading to processes like high harmonic generation, attosecond pulse generation, non-sequential double ionization, laser-induced electron diffraction, and so on. Usually, the energy of the recolliding electron is too low to affect the nucleus, but for thorium-229, the nuclear excitation channel is open. This we first use a semi-classical calculation to estimate this recollision-induced nuclear excitation process. That at each possible recollision time, T of R, the nuclear excitation rate, gamma, is a product of sigma, which is electron excitation cross-section with this recollision energy, E of R, and the recolliding electron flux, J, at the time of the recollision. Therefore, the first term, sigma, is from nuclear physics, and the second term, the electron flux, is from strong field atomic physics. So we see from this formula how these two research areas are combined. The electron excitation cross-section sigma has been calculated by Professor Kalia and also by us using Dirac distorted wave-Born approximation. Roughly, the cross-section is on the order of 10 to the minus 27 centimeter squared, or 1 millibarn. It has a very weak ionic state dependency. We see that they are very close to each other, except maybe for the neutron atom case, there is a deviation, small deviation near the threshold. And also the cross-section decrease with electron energy. Therefore, the electrons with energies around 10 electron volts are most efficient in the isomeric excitation. The reclining electron flux can be estimated using a standard strong field technique that tunneling ionization plus classical trajectory propagation. So at each time, electron may be tunneled out at the tunneling exit point with some initial momentum distribution perpendicular to the polarization direction. And then the trajectory subsequent evolution is propagated using classical mechanics. Basically, at each time a bunch of electron trajectories are initiated, each is assigned a weight according to the ADK rate and the momentum, perpendicular momentum distribution. Then we collect those trajectory that recline and recline within a critical radius, ROC. Outside this radius, the reclining trajectory, we say, is too soft for isomeric excitation. So without going into the details, I just tell you that this ROC is roughly 1 atomic unit. So basically, we get reclining electron fluxes like this. For this laser pulse, 30 femtosecond, peak intensity 10 to the 14 watts per square centimeter. We have reclining electron flux for the first electron, which comes earlier, the second electron, the third electron. The first 2 electrons are fully emitted, and the third electron with this intensity is only partially emitted. Therefore, it is lower in magnitude than the other 2 electrons. Then at each time we have the flux, and then multiply by the excitation cross-section, we have at each time the nuclear excitation rate, gamma. Then if we integrate that rate over time, we get the probability of nuclear excitation at each time. Then at the end of the pulse, for this intensity, we get a total excitation probability roughly a few times, 4 times 10 to the minus 12. This semi-classical calculation, of course, has its limitation because it is based on the recollision picture. It is picture-based, and it only increases laser-driven free electron transition because recollision is a free transition. Other processes like free bond electronic transition may also contribute to the nuclear excitation, but they are not included in the semi-classical calculation. Therefore, a quantum mechanical theory is needed. That is what we did recently. We built a quantum mechanical theory with 3. It's a tripartite interaction between the nucleus, electron, and the laser field, the total Hamiltonian, the electron part, nucleus part, electron-nuclear coupling, electron-laser coupling, nuclear-laser coupling, and these couplings can be expanded using multiple moments. Basically, we can use perturbative treatment for the nuclear-laser coupling, electron-nuclear coupling, but we have to use non-perturbative treatment for the electron-laser coupling because this is very strong. And we use a single active electron approximation for each electron. So this theory is very similar to solve the time-dependent, actually Dirac equation, but with the nuclear state space included. So it is more difficult than just for the strong field atomic case. Relativistic effect is important due to the large Z, which is 90 for thorium 229. Without going to the details of the formulas, I just show a few results. The first result is for a 800 nanometer. We have the same peak intensity of 10 to the 14th watts per square centimeter. But here we use a much shorter pulse because this calculation is very difficult. The pulse has 5 cycles, and we see this is for the first electron, the second electron, and the third electron. We see that the excitation probability during the laser pulse is more complicated than the semi-classical model. But we are interested in, at the end of the pulse, what is the nuclear excitation probability? We can get excitation probability for the first electron, the second electron, the third electron, and in the end, we get a total excitation probability roughly 9 times 10 to the minus 12. Remember, semi-classical results gives 4 times 10 to the minus 12. So we think, okay, the semi-classical result is not too bad. It's on the same order of magnitude. It's within a factor of 2 or 3 to the quantum result. And of course, the semi-classical result only include part of the mechanism, only include a free excitation. So we think these numbers are pretty trustable. If we change the laser wavelength to 400 nanometer, we get a higher excitation probability, roughly 3 times higher, about 2.7 times 10 to the minus 11. So using femtosecond laser pulses for the isomeric excitation has the following advantages. It is in terms of efficiency, roughly it is 10 to the minus 11 per femtosecond pulse for nucleus. Remember the 29 kV synchrotron excitation method, it gives 10 to the minus 11 per second. Roughly 1 femtosecond laser pulse gives a nuclear excitation comparable to the synchrotron does in 1 second. And this method only requires a tabletop laser system instead of big facilities. And it does not require resonant condition because it is a laser-driven electronic excitation. It does not require resonant condition. In contrast, those optical excitation, they need to search for strict resonant conditions, including, for example, the 29 synchrotron case, they need to search for resonance. And the isomeric excitation is well timed. It only happened within the femtosecond laser pulse, not randomly distributed over all time. Therefore, this may be useful in the future for coherent operation of the nuclear excitation. So in conclusion, we have considered isomeric excitation of thorium 229 using femtosecond laser pulses. And we first use a semi-classical model based on the recollision picture. And then we developed a quantum theory based on the tripartite interaction between the nucleus, the electrons, and laser field. And the quantum theory includes intrinsically laser-driven free bond electronic transitions. And the recollision model only includes the the free electronic transitions. So the take-home message we want to deliver is that the probability of nuclear excitation is roughly 10 to the minus 11 per femtosecond pulse per nucleus. And finally, I acknowledge my collaborators, 2 of my students, Mr. Wu Wang and Mr. Hanxu Zhang. And for that, thank you for your attention.
Yeah, thanks very much for a very nice talk, presentation, and also here, congratulations on this nice idea also, and these very nice results you get. I guess there are questions on this. I have a few questions if no one wants to start. Just again, speak up, just unmute, type in chat or raise hand. Okay, then I'll start with my question, gives me the opportunity. So have you looked at, since you do this quantum mechanically, this is exciting, you would expect if you hit this resonance of the nucleus, that if you, for example, make your pulse longer and longer, wouldn't you expect the population to grow quadratically as a function of the pulse duration? Have you checked for this?
Yes, we have checked that with longer pulse, at least using the semi-classical method.
Mm-hmm.
Roughly we get similar excitation probability, because if we think in terms of recollection, recollection is we get one recollection per half cycle. Each half cycle is very similar to each other. So we haven't observed any dramatic increase if we increase the later pulse.
Okay, because I would have thought if it's happening coherently, and in the quantum theory, of course, you keep the phase of this transition. This could be also, at some point at least, I would think there is a coherence effect in the excitation. So maybe one has to search for this a little bit to find this resonant condition, but it may happen at some point. Would be very exciting.
Yeah. So for the quantum calculation, we only have results for very short later pulse because the calculation is very big. So we will look into that. Yeah, that's a good one.
Thanks a lot. Sounds really fascinating. Okay, there is a question, Vasily, in the audience. Just unmute and ask.
So, am I right that in the semi-classical approach, the whole job is done by the second electron, and this is natural because the first electron has too low ionization potential?
That's right.
Right. And in the quantum approach, it's qualitatively different. The whole job is done by the first electron, and this seems me strange because it has low ionization potential. So what is the explanation?
Yeah, that's a good, very good point. Yes, because in the semi-classical case, it is based on the recollection picture. So we assume that it's only from recollection, but the first electron is ionized too early. So the recollection energy is less than 8.3 eV. That's why you see there with this intensity almost no contribution from the first electron. But in the quantum theory, other channels are also include free bond electronic transition. Therefore, we see the first electron has a quite major contribution. So I would answer that this is because the inclusion of other electronic channels.
Okay, thanks. There's Barry. You have a question?
I do. It's a beautiful talk. Thank you very much. My question, I know you were motivated by 800 nanometers and 5 cycles by experimental techniques, but I think clearly because there's so much flexibility with rescattering as you change the wavelength and you change the intensities, what do you predict could be an upper number or a higher number if one allows that flexibility? Even by going, for example, to like the FELs, right, where you can still get rescattering because the wave function doesn't have time to spread.
Mm-hmm. Yeah, thank you. If we have in the quantum theory, we have 5 cycles because the computation is very big. If we actually in the semi-classical calculation, we actually checked what happened if we use a much shorter later pulse. In fact, very interestingly, if we use a much shorter later pulse, like a few cycles, 10 femtosecond, something like that, the first electron becomes useful again, because then the recollection energy is not what we usually assume, 3.17 EV UP, right? If the pulse is very short, the first electron, at time ionization, at time recollection, it feels a very different laser field. We see that then the first electron can have the chance to have a recollection energy higher than 8 EV. So then what we find from the same classical calculation is if we shorten the laser pulse, we get a higher excitation probability.
Okay, thank you. But I was also just referring to the fact that you could change your drive frequency to 100 nanometers, 50 nanometers, and just see what you could potentially get as an upper number as we try to go to these like nuclear excitation processes.
Yeah, our experience is that if we go to 100 nanometer, 200 nanometer, then recollision probably becomes less important. Then with those wavelengths, bond-bond transition, free bond transition becomes contributing more to the nuclear excitation than the free transition. So recollision becomes a less important process with those wavelengths.
Okay, thank you.
Thanks very much. And I think currently I don't see any more raised hands, and we are also at the end of our session time. So let's thank all our speakers again of this session. And then let me also recommend the next plenary session that starts at 2 p.m. GMT, again with the topic of the thorium isomer 229, from the atomic to the nuclear clock, given by Peter Tirolf. So this should be also interesting, directly connects to the talk we've just heard. So thanks again for everyone, also for the discussions, and see you hopefully soon. Bye-bye.
Bye.
Bye-bye, thanks.
Thank you. Anatoly, if you're still here, I had a question, in fact, if you don't mind. If you're still listening by any chance, then I would just ask if you're already disconnected or busy with some other things, that's also fine. Seems you're already in your next meeting. Anyhow, very much enjoyed your talk. Thanks.